So, what I want to do is give you guys a. I know that the collisions is not until the next class, and I know. So I said to do is do a practice day, and it can still be a practice day. But I want to finish this, which is going to include covering collisions, and then whatever time is left today and the next 2 days will just be practice days. Why are the book bags in my desk? Confused. All right. Just do one thing here really quick. I do want to make one quick announcement. Guys, please be quiet. I do want to make one very quick announcement. My recordings, what the hell? No videos. Not this stuff. I do want to make a very quick announcement though. A lot of you guys, when we do have practice days, are not turning in anything. And because of that, remember every practice day that goes by, because I had to reduce the number of levels points per day, although I'm actually making it 80 points per day lately. But it's still, every day that goes by that you don't turn in something in, you kind of fall 2 levels behind. And at this rate, some of you guys will literally, even if the test is what's worth the most, you literally get C's, maybe even D's, if you stop turning things in. You have to turn in things, all right? It's not okay to have a practice day, just not turn in anything. A lot of you guys are falling levels behind, like a lot of levels behind, and I'm worried about that, all right? Remember, I just sent a message. Did you guys get my message on Sally? All right? I know. I want to kind of vent about that. I can't, this doesn't really affect you guys much because honestly, to be completely honest, physics honest is in the back of my mind when it comes to planning. I just kind of, a lot of times I wing it because, you know, I only have one of this class, so it's like, it's a lot of work to prep for one class and, you know, so the 6 I have. But it doesn't mean I don't prep for it, right? I was worried about you guys this morning, that's why I made the changes. But having said that, that hour that I have here after school is here for all of you guys. You can always come, and a lot of you guys don't come. So if you're really behind and you're not taking advantage of it, make sure you start taking advantage of it. But don't think that I'm going to be able to necessarily sit down with you and help, all right? On practice days is the best time to get my attention, though. Put your name on the board. If you need to talk to me, I'll go and talk to you. I'll help you if you need help. I'll help you with how you need to figure out studying and stuff like that to do better on the tests, do better on the assignments. But honestly, I'm not really worried about test performance here, you know, with the curve and everything else. You guys did all right. I'm more worried about the practice days and the slacking that's happening during them. So on the next practice day, the other thing too is that I'm worried about is that you need to do more active work rather than just, we talked about that already. But anyways, what I'm talking about with the practice day, you need to do it. I'm going to actually have to start, if this doesn't get better, to start like mandating a quiet environment. Because a lot of you guys are fooling around too much, and that's what's consuming your time. Meanwhile, I have other people that in one practice day they do like 30 math problems, and then they get all the points, more than the points they need. Right? So, yeah, it's fine if you're doing that. But what I'm saying is that there are people who are not doing work seriously, and that's actually hurting. And it's okay if you need more time because, you know, 1 hour is not enough to get the 80 points, that's fine. You can have more time. You can even finish at home for last points, but you can finish at home. You need to do it. A lot of you guys are falling behind. You definitely cannot afford to fail quizzes, not do the practice, not turn in notes, and not do the practice. Then this is really bad. Having said that, the grades don't look bad for physics honors. They look all right. But I know there's some of you guys that are much better students than that. So you gotta do better than where you're at. So, what was the first one that I skipped here? Because I do want to talk about everything now. I skipped 3. All right. So then, remember when we talked about collisions and I said there's 3 types of scenarios that involve momentum that we have to talk about, right? Well, actually, there's 4, right? So there's 4 situations. On the first situation, all you're going to need is this formula right here, which we talked about last time, right? Which is, what does this mean? Force applied over a certain period of time. What's the key term that this is about? Impulse. Very good. Now, impulse, think of it as an apply a force for a certain period of time, it's going to cause a thing to gain momentum, right? That's the other thing. This impulse thing equals the change in momentum, which is, of course, that, right? Or you can write it like V final minus V initial. Now remember, when you have these in physics, when you have these really long inequalities, what that means is that you can get any one equal to any other equals, right? So for example, you can say impulse equals that, right? You can also say that F delta T equals that, right? So all of them, any one pair can be useful for solving problems, right? So the first kind of problem is just about that. A force applied over a period of time, we're going to see some at the end here, causing a change in momentum. The second kinds of problems, which fall in three types, are those kinds of system interaction problems. All right? So for those kind of problems, you're going to have three types. The first one is you have two things heading towards each other, and they kind of sticking together. I talked about that. We even talked about one of them. When you have a truck, right? And I tried to demonstrate it, but the friction got in the way. But if you have someone that has that's traveling at a certain velocity, and then all of a sudden a bunch of extra mass gets dumped in that person, the rule says momentum must be conserved. In fact, that is the only four things you need to know about that. Change in momentum equals zero. Always. You cannot change momentum of a system from the system itself unless a force acts from outside the system, right? So that means if you have, for example, like I said, the problem that we looked at last time, you have a truck and they dump a bunch of coal on the train, right? On the truck as the truck is passing by. Now, if there was no force acting on it, so remember there was no force acting on it, and the momentum is supposed to be conserved, the only way that that's possible, if you add a mass, you have to drop the velocity, right? So that's the situation that we talked about. So the first kind of scenario is going to be when things combine. And the key for that, for these kinds of problems, right, is that when you look at momentum before, momentum after, so you're going to have to, we're going to see another example of that in a second, but that's the first type. The second type is when you have two things heading towards each other, colliding with each other, and then bouncing off each other. All right? And then the third type of problem is going to have things which work together kind of splitting up. I call them the blowing up thing, all right, or the explosion one, all right? So you have this before and after of these situations here, right? And these are the three kind of problems you're going to see. But in all problems, that formula is one of their governors, right? For example, if I was doing this one, it would be the momentum of the first object at the start plus the momentum times velocity. This is the momentum of the first object, right? Plus the mass of the second and the velocity of the second. That's the momentum of the second object at the start. Will have to be equal to the end here. But look at what happens there. At the end, they combine, right? And now they will have only a single velocity after the fact, because I'll call it the velocity after. Velocity 3 of this, right? Because velocity of the first object, velocity of the second object, and the mass of them. So the momentum you have over here has to be equal to the momentum you have over there, right? And so that is the kind of situation that happens here. On this one, it would be the same kind of scenario. Mass of the first object, velocity of the first object, plus the mass of the second object, velocity of the second object, right? Will have to be equal. The mass of the first object times the velocity of the first object after, right? Plus the mass of the second object, velocity of the second object after, right? So in other words, whatever momentum you have over here has to be there at the end. And since you have two separate objects in the beginning, two separate objects at the end, it will have to be like that. We're going to see types of problems like this in a second. Remember, you have to have this on your finger, a document. You know it's not part of any question, but you're supposed to be writing this stuff down. And then this one is the opposite of that one. You have something that was together at the start, right? Something that was together at the start, right? It may have a certain velocity. Call it velocity 1. And then it's split up at the end. Right? Now think about what this means though. Let's say this thing wasn't moving. So what is the velocity there going to be? 0. So this whole thing is 0, which means these things must what? They must be opposite, right? So whatever number this is, this must be the opposite to cancel out. Does that make sense? And that's kind of how a lot of scenarios of explosions are like that. So wherever momentum one gains this way, they will supposed to gain that way. So that the momentum is conserved. Now, remember you can gain kinetic energy or you can lose kinetic energy in scenarios. That's the other thing now. So now parallel to all of this, there's changes in energy. Right? So now you have to remember this. Every time the change in kinetic energy is zero, that's called an elastic phenomenon. Right? It's not a collision. That doesn't really exist. Alright? There are some particle physics interactions which are considered to be elastic. Like when certain particles collide in a particle accelerator or inside the flame of a star. But even then, some of the energy goes to something else. Right? So there's not really, but conceptually, you can talk about things, a situation where that would happen. Meanwhile, you have other situations where the change in kinetic energy is different from zero. You either lose kinetic energy or you gain kinetic energy. Right? In a situation like this, for example, you're going to gain kinetic energy. So this one typically, right? This one specifically, you tend to gain kinetic energy, right? If you go stop and then you blew up like that, right? You tend to gain kinetic energy. Like two people pushing up each other, right? You gain kinetic energy, but no momentum, right? So you also gain momentum. So, in other situations like you can either just be completely inelastic or a partial inelastic collision. And the situation there is the difference is that when they kind of merge like that, it's going to be completely inelastic. That's by definition. What happens when they kind of merge like that? They collide and become one. It's completely inelastic. Right? There's a lot of kinetic energy loss in those situations. Right? Now, when they bounce off each other, they could be elastic or partially inelastic. Theoretically, there is no true elastic, right? So they're all partially inelastic, right? So that explains basically the whole thing that the chapter talks about that you guys are supposed to read for next time, all right? So you're still supposed to read it, by the way. You're still supposed to do it. And remember, if you just read it, you're not going to get the whole picture. We do a review here in class. So if you don't, this is why you're perhaps not doing so well in the test if you're worried about that, all right? If all you're doing is reading this textbook, so Therese, all that stuff in the back, you're going to throw it away. No worry about washing it. You're just putting it away, right? And then we have to set up for lab 5, which is the one that I'm showing this. And for that, most of the stuff that you take down on the lab itself, right? The cops and everything else. Or we use that they're sorting about down in the solution, right? That's part of what the lab says. You know, so you infuse, remember that? You infuse the whole thing and let it go, the plunger thing. So the only harder part is that. So everything else they can kind of figure it out. So what I was saying. Okay, so if you're having trouble, all right, it's because this is only covering the major concepts. It's not covering everything, all right? And it's not covering slow enough for you to get every single thing in detail. So if you want to start doing better, it's not just reading the textbook and doing the practice the night before, right? You got to go to the physics classroom. You got to watch a couple of tutorial videos. So over here, it's not the only time you're learning, okay? So this time it's before the topic, but it's still. Anyways, this is basically the premise of all of it. So now with that in mind, we skip to which one? Number what? 4. A bag undergoes a one-dimensional elastic collision. What does that mean? Elastic collision. No kinetic energy loss. That means I'm going to hit the wall and bounce back from the wall with just as much kinetic energy as I had before. Right? Now, that doesn't usually ever happen. Right? So, let me just demonstrate. Even if I had a very, very rubbery or very bouncy ball. Have you ever seen Flubber, the movie, the older movie? Right? That thing is not even elastic. That actually gains energy every time it collides. Right? So it goes faster and faster. It's like creating energy out of nothing, though, right? So that's why it doesn't make any sense. By the way, I love doing inspirational, cool physics side talks. There is a machine out there that supposedly creates momentum out of nowhere. All right? All right? It's called, but it's not one of those fantastic, on the internet, look, I made a professional machine, motion machine, kind of thing. It's actually real physics that nobody understands. Now, people are so dubious of whether this thing is real that right now, nobody considers real science yet. Because nobody understands the theory behind it, and people are still questioning the actual evidence, right? Just the other day, I was telling my students from biology that when they're doing this in the lab yesterday, they forgot to get averages, right? And then I said, well, if you forgot to get averages, you don't have any idea of anything. Because if you only measure something once, you have no idea, right? That's part of why people say it's wrong, because they say you haven't replicated in a different lab yet. You haven't published in a peer-reviewed article research. So nobody really knows. It sounds very iffy. You know what I'm saying? And we need to see how you're doing it. Other people have to do it again to make sure it's right. But look how cool this is. So, this is a side topic, but it's okay, right? What is nothing? No, seriously, I'm going to start with that. Give me an example of nothing. My social life. That's all. All right, I love that.
My love life.
I love
life, yeah.
No, I love those. Those are funny. But, oh, by the way, you're supposed to pass out Legos doing this. So, the two people that made jokes, those are pretty good. You can have a Lego. All right? Nothing. Is, a long time ago, when people wanted to go to, somebody proposed that we could perhaps fly to the moon. But then in order to do that, the same kind of stuff that was out here needed to be between here and the moon. Now we know that's not true because the atmosphere stopped, right? So you can't fly to the moon. You have to go in a rocket, right? But at one point, a philosopher, a scientist said, perhaps you could fly to the moon so long as the air stays all just between here and the moon. He said, of course, there was sacrilegious, he didn't go to hell, all that stuff, but that's a different story. All right? Now, at one point, people thought there was nothing between you and me. Later, we figured out there was air between you and me. Then, what about her between here and the moon? Is there nothing? What is there between here and the moon? Empty space, no? So that's like that. Technically, there's a bunch of particles streaming from the sun, solar winds. And technically, it's not nothing. It's actually, the vacuum is not nothing. It's full of stuff. Now, is it really nothing? And say, for example, there's gravitational fields there, electrostatic fields there. Actual forces actually happening in space. That's not really nothing. So most physicists today say that that's not nothing. Even if it was truly a vacuum, it wouldn't be nothing. Are you with me? What about outside the universe? Is that nothing? Right? It's hard to think about that, right? But regardless of that, without getting too complicated into nothing, let's just talk about vacuum, right? Or empty space. The space between here and the moon is, forget the solar winds, forget the fields. We're talking about the matter. By the way, remember we're talking about this last class. Matter and energy are the same thing, right? E equals mc squared. So whenever you have energy, you have matter. And if you don't have matter, but you have energy, you do have matter, just in a different form, right? So, it's hard to understand, but we'll learn more about that at the end of the year. So that means empty space. If there's energy there, like say, for example, light. Light is photons, right? So there's no mass, but that's energy. And therefore, it's as if it was mass. So you can talk about gravity as causing light as causing gravity, right? Because gravity it's caused by mass, right? But light is energy, and so energy has mass in a way, equivalent of mass. So light can cause gravity. So that's why the thing about fields matters. If there's a field, it's not nothing. But forget that. I'm not talking about that. I'm talking about something cooler than that. Empty space. Nothing. The blackness of space. Not real nothing, but, that's close to nothing as most people understand. It's actually not empty. Every single second, this is really bizarre, but it's actually true. Right? Every single second, particles pop into existence out of nowhere and then go away again. Now, that seems to contradict the third law of thermodynamics that says matter is created or destroyed. All right? Are you with me? However, this is something people don't understand. Now, this is not just between here and the moon and the empty vacuum of space. This is everywhere. Because between me and this table, there's gas. There's gas molecules, right? But what is gas really? Molecules of O2, right? But if you look at oxygen, So you have an atom of oxygen here, and another one there, and there's electrons in between. But then, let's say this is the nucleus, the protons. And let's say these are the electrons pulling around. What's in between? Just empty space. So there's not just empty space in the outer space, there's empty space everywhere. Does that make sense? Tiny little amounts of empty space, but if you really think about it, most of the space here is empty. Because most of the space is the space in between where the electrons aren't. Although technically, that's another thing, if you try to figure out where electrons are, they're technically everywhere and nowhere at the same time in the atom. Alright? We'll learn more about that at the end of the year as well. Okay? No. The cool thing, no, this is actually cool. Because electrons, they don't have an actual location. There's have you heard about the Heisenberg uncertainty principle? Anybody heard about this? It's the idea that you cannot measure energy and time at the same time. It's impossible. Or that you cannot measure momentum and position at the same time. There you go, momentum. So in other words, you can tell where something is, but then you can't tell how fast it's moving. Or you can tell how fast something, or not just how fast something's moving, but also its mass, right? Because the momentum has that as well. So either you know the mass and velocity, or you know the position. But if you determine the position very well, you can determine the momentum, right? Very well, you cannot determine the position very well. An easy way to think about that is this. If you shine a light to see an electron, the electron will absorb the light and jump somewhere else. So you can never see an electron. Does that make sense? So you can never actually measure where the electron is. Does that make sense? So that, in other words, if you try to think about where the electron is, well, there's very second the electron was there. But if you look over there, it will probably be there. If you look over there, it will probably be there. That's the weird thing about it. So technically, the electron doesn't really have a position. It has a certain statistical probability of being somewhere. Right? So the electron is like a wave that is between here and here somewhere. Are you with me? So it has a wave function. Now here's a weird cool thing. You're not actually here. You're between here and there. It's just that this is less observable than larger things. But with smaller things, this is so real in fact, this bizarre thing happens. There's a wall here. There's an electron going towards the wall. It's a wave function, right? It's not actually a particle. It's something that's between here and here. You cannot determine the position very accurately, correct? Look how crazy this is. There's a wall here, okay? There's a wall. So the electron comes. It's actually on the other side. So electrons teleport across walls. Now, you know why? Because think about it. If the electron could be anywhere in this region, right? By the time it gets here, it could be anywhere in this region. Correct? So technically, it could be on the other side of the wall, and technically it is. This is called quantum tunneling. Now, this sounds insane, right? But there's actually technology that uses this. All right? There's a quantum tunneling microscope, which allows us to see entirely very small little things. It's short distances. And you can actually use that to measure short distances. It's insane. We'll learn more about this at the end of the year. But the cool thing about that, this crazy kind of advanced physics that most people don't even know it's real, is that this is already 100 years old. People figured this in the 1930s. All right? Now, I know. But okay, so let's going back to the empty space. So the way that happens is that particles pop into existence, yes, but there's a rule. For every electron that pops in, an anti-electron pops in. An anti-electron is antimatter. It's the polar opposite of the electron. And in the very next second, they annihilate each other and cease to exist again. So it's like, do they really exist? No, because the very next second they don't exist. If you ask them, they're called virtual particles. Particles that don't really exist, but they do exist. Now you see the paradox I just said out loud? It seems confusing, but it's not that confusing. It's okay in quantum physics for things to be completely opposite and true at the same time. So the electron is here and it's not here. It's there and nowhere. Those kinds of things actually make sense. All right? In the mathematics of quantum physics. That's an example of it. So here's the cool thing about this though. Can you use something that don't exist and have a real effect? I already taught you guys about this. Does this exist? No, it does not exist. That does not exist. All right? However, if you do that, that's -1. So you can use something that don't exist to get something that exists out of it. So it doesn't exist. Now, I love that example because it makes it really apparent that things are not that simple. Correct? That sometimes imaginary things are real things in some sort of way. With that sense, here's what's cool about this, all right? It's a machine that does things without breaking the momentum law. Check this out. With very close, two metal plates, very close to each other. Now this is incredibly close, okay? We're talking about nanometers apart, the two metal plates, right? Now remember, these particles pop into and out of existence. But here's the thing. If this space is very small, the particle that pops in here can't just be any particle, because it's confined by the small space that it has to pop into. So a particle that has a wave function bigger than that space cannot pop in that space. Does that make sense? This limits the size of the particles that form in there. Alright, are you with me? Out here though, since it's unconstrained, the particles can just form. Bigger particles can form. Right? What that means is that bigger particles form here than in here. That creates a kind of pressure that literally makes the plates touch. This is called the Casimir Effect, and this actually happens. Literally, two metal plates. Now, of course, you would think gravity is bringing them closer, but you can compute the effect of gravity on those plates. You can actually mathematically quantify how much gravity exists within the plates. And even with that gravity, right? So there's actually things you can do too. You can charge the plates, so you can make one plate positive, one plate negative, just enough to counteract gravity, so that way gravity should not be, as much as gravity is trying to bring them closer, electrostatics is trying to push them apart, and therefore, you know, they don't pull apart. Or you can quantify the effect of gravity. The point is, when you do the math, it doesn't add up. The plates are not closing in because of gravity. They're closing in because something is pushing them closer. You can actually do this on a little water tank. So you literally make waves on both sides of the water, and then waves will form because of the collisions inside of the plates too, and it will cause it to close. So it's an analogous to this phenomenon. I'll show you at the end here when we go back to this. I'll show you a video of it. But what's crazy about this is that this is true, the effect of virtual particles. So there's a machine called the EM drive that supposedly breaks conservation of a because it's basically a conical structure like this, and then microwaves are emitted inside the cavity. But because of the shape of the cavity, and it's something analogous to this Casimir effect, there is a more pressure on one side than the other because of the virtual particles that come into existence. And that causes the thing to be pushed forward without any engine, without any fuel of any sort. You just need to power the microwave generators, and you can use solar power for that. So you can put this in a spaceship, put it in out of space, powered by the sunlight, that would just propel itself indefinitely. Now, theoretically. The problem is, this machine creates thrust that's so small. Now here's where it gets tricky. The thrust of this is micro newtons of force. Alright? You know what I'm trying to say? It's very, very tiny. The machine that measures, it's like this. They put it in a machine that pivots. So like, you put the thing here, and there's an arm, and then you're trying to see if the thing is rotating. So the engine is over here, trying to flip this thing this way. And if by measuring the angle, you can figure out if it's actually being thrusted or not. Right? But the thrust is so small that it's actually pushed the limit of the precision the machine can actually measure. So then it could just be an error. Right? That means that it's not actually causing thrust. It's just the machine's error is so close to the actual value of the thrust. Right? So it's like saying, oh, this is a meter, right? But I use something that is, it's like saying it's 1.5 meters long, but I use something that's only a meter to measure that. And so it's hard to tell that it's exact, the precision is not there. So that's why there's some big criticism that people have about it. And yet there's a video online, if you look at this, there's a Chinese that made a bigger version of it. And there's a video online, and this thing just like sits there spinning. Now, people say, that's not, a small amount of thrust over a long period of time. It gathers up and you actually start spinning. So they say it's real. Whether it's real or not, it's not still to be figured out. But here's the cool thing about it. Conservation of momentum, right? Is it really breaking the rules? Not so much. It's just there's something else going on. There is a force, a kind of pressure that's being caused by these particles that don't exist, right? But anyways, going back to momentum. We were talking about hitting a wall elastically, correct? So let's say you hit the wall and you bounce completely back from it. This is elastic or inelastic? Elastic or inelastic? Remember, elastic, you don't lose any energy. Right. Think about how much, is there an easy way to figure out how much energy I lost? Think about it. So I drop from this height, and I stop at this height. The difference in potential here is how much I lost. Right? Exactly. It's actually easy. So it's actually directly related to the height. So if I lost 40% of the height, it's like I lost 40% of the energy. And look at it. Am I going halfway back up or less than halfway? Watch. So most of the energy is going somewhere else. Where? Sound, seismic waves, things like that. So there's definitely a non-conservative force, friction, sound waves, but heat being produced here, that's wasting that. Most collisions will be like that. But they're saying this thing is hitting the wall and bouncing back elastically. Now, is the sum, okay, so where's it here? This one? All right, the velocity of the ball is reversed while the wall remains stationary. Saying why this does not violate conservation of momentum. Now, here's the thing. Momentum has to be conserved. So it's a collision of sorts, and it's kind of like this one when it bounces, except the wall doesn't move, and it wasn't moving to begin with, right? So we got to use something like this to think about what's happening, right? So let's think about what's happening. The ball comes in with a positive velocity, hits the wall. The wall doesn't have any velocity, so it has no momentum. Does that make sense? At the end, does the wall have momentum as well? No, correct? So it seems as if this is 0, and this is also 0. And then you have a value here of some sort. Now at the end, it says the ball comes back with the opposite velocity, exactly how much you had before, right? So that means this would be negative v. The same v as this one, but negative. Are you with me? Now, listen a second. So let's talk about change in momentum here. Change in momentum. Let's calculate it. If this was, say, mv, and then afterwards all you have is negative mv, they don't cancel out. This is not the same thing as this one. In fact, what you have here is something else entirely, right? The momentum is changing. At first, by how much? Think about it. I had mv momentum, and now I have negative mv momentum. By how much the momentum changed total here? Twice. It's like I lost 1 mv to go to 0, and I lost another one to go to a negative mv. So it looks like the change in momentum is negative 2 mv. At least the ball's change momentum is that. So if the ball changed by negative 2 mv, the wall's supposed to have gained 2 mv. Otherwise, you're breaking the rule. But is the wall gaining? No, it's just sitting there. So now we have a problem. That seems to contradict the laws of conservation of momentum. Is it the same situation of a machine? Not really. Remember, in what situation is momentum conserved? When is this true? I said earlier today. Who can help out? When is the momentum of a system conserved? No outside force act on it. So now we have to figure out, is there a force here that we're not seeing? Okay, so think about it. I hit the wall with mv. If I come back with negative mv, I suffer a negative 2 mv change, which means the wall is supposed to gain 2 mv. And that's still there, not even moving. Why isn't the wall moving? According to this, there's got to be a force acting here. Okay? Yes, you got to use your head like this, and I say, it's not that hard to just think about it, right? So you're hitting the wall, boom, and you're coming back with the opposite momentum. That means you have a negative 2 mv change in momentum here, which means the wall's supposed to gain 2 mv. Right? But it doesn't seem to move at all though. So the only way this is true, there's got to be a force acting here. Why is the wall not moving? What did you say? More friction in the ball. Well, how much friction is acting on the ball if you decrease air resistance? None. What about the wall? Is there some sort of friction holding the wall in place? Of course. The wall's being held in place to the floor. There's friction there. Right? And that's what's stopping it. What if you did this on ice? Would the wall move back? Right. The wall's fine. The ceiling and the floor are ice. No friction in the ceiling or here. Will the wall move back? So, along the same lines, a mosquito, tiny little mosquito, hits a truck that's sitting on ice. Okay? Now, let's say there's no friction. Completely no friction. The mosquito becomes one with the truck. So you had a bunch of momentum in the mosquito, not much because its mass is very small. But then you hit the truck. It's something like this, isn't it? It's something like that one, right? So that had momentum, that had none. But you're still supposed to have momentum here. Not much, because the mass of the truck is going to be so big that velocity is not going to change much. Are you with me? But the key thing is, should the truck gain some velocity from that? Yes. But why it doesn't in most situations? Because it's what? There's friction. So you have to delete all friction to actually make the momentum conservation happen. Does that make sense? The moment non-conservative forces are acting, you're going to catch a lot. So like in the machinery we were talking about, for example, people start talking about, well, you're gaining momentum, right? Maybe it's not because of this breaking of the conservation, or maybe you're shaking, or some sort of electromagnetic field that you're not accounting for. In a room that is completely like anti, where the whole room floats, right? It's weird. I don't know how to explain it. It's like the actual room is raised up in a device that prevents shaking. So when the earth shakes, the room just sits there. You know? And it's like anti-seismological movement room. They have to repeat the experiment in there to make sure, and they did that, and they still found the effect. Then people said, well, you can't cancel out the electromagnetic field of the earth. Maybe there's something going on there since you're producing EM waves. So they have to now try to create a magnetic insulation to prevent the magnetic field of the earth from having an effect on the experiment. Because remember, this is such a small thrust. It could be something else that they don't realize that's causing it. So they're trying to figure that out. All right. Is that clear that momentum is conserved here? You just forgot about the right? So that's what we're looking at number 4. Number 5. On an air track, a mass of m and speed v moving along the deck collide with a stationary cart. All right? So what situation is that? We have a mass hitting something that's colliding. Look. Something, and that's stopped. That's not going to have any momentum, right? So we're going to have the mass and its velocity v. Anybody clear on that? That's the momentum that I have at the beginning. The mass m and the velocity v. They actually give us that. And they say the cart has a mass of m over 3, but what's the velocity of the cart? This velocity. It's stationary, so what's the velocity of the cart? Guys, wake up. What's the velocity of the cart?
0.
All right, so how much momentum does that have? 0. So what is the momentum that I have at the start? Call it the momentum, the initial momentum. Just adding both of them together, which is what? MV. Oh, this one has momentum. Right? Yeah, that's what I'm saying. Initial momentum is the sum of the momentums of the particles in the system, right? So this has none, and this has MV, so the total is MV. So according to the rule, if no force acts, what should be the momentum at the end? No change, right? So what should be the momentum at the end, according to the rules? If no actual force acts here, it should still be? No, it's not 0, it's MV. Right? Okay. Now, after the collision, the first cart has a speed of v over 2. All right, so then this is after collision now, right? So after the collision, we're doing the aftermath now. We don't really know which way it's going. Actually, we do, because it says it's going with a speed of v over 2. That's speed, so we don't know the direction. But we know this has v over 2, right? That's a lot. And then the first card has a mass of m. So do we know the momentum of the first object already? What's momentum? Momentum is m times v, right? So what's the momentum of this object? M times v over 2. Now, what is the mass of the other object? They gave it to us. It's m over 3, right? Now, this total is still supposed to be that. Does that make sense? So that's what you just set up an equation to find the velocity of this guy here that we're trying to figure out. Velocity 2, right? So it's supposed to still be mv. That's the starting point. I have something that I know is going at mv over 2. I also know that this is m over 3 v that I want to find out. So now I just solve it. Right? So how do I do that? I can send this to the other side, right? And what does that become on the other side? So it's just sorting back out and tells you how much.
And then what about
2%, so it's like under 300 mLs, which is 300 grams. 0.2%, which is like 3? No, 6 grams. That's the sodium bicarbonate, and the rest is water. So it'll be 6 grams of sodium bicarbonate to 294 mLs. All right, make it on a LMI flask, okay?
All right.
So where are we? If I send this to the other side, what do I get? mv over 2 equals m over 3 v2. So what do I do now? Can I multiply? Can I take m out? Because it's on both sides. Okay. What else can I do? Multiply both sides by 3, right? And then I get what? That v2 equals 3.5 v. Does that make sense? So that means the car is going 1.5 times the initial velocity that the other car used to have. Right? Now let's see if that makes sense. You collide it with a smaller mass, right? And then the original car kept half the speed. So the other car is supposed to keep half of that momentum too, but he has a smaller mass, so it's going to go faster. Does that make sense? Right? So that's how you need to look at this. But you see, the key to solve these problems, you basically set up an equation where the momentum at the start has to be equal to the momentum at the end. It's always like that. And you just ask yourself, how much momentum does they have at the beginning, how much will they have at the end? Did we do 6 already, right? Did we do 7? 8? 8 we didn't do. Did we do 8?
Yeah.
9, did we do 9? So now, 2 unequal masses. But how does the impulse impart on the smaller mass by the larger mass compared to the impulse imparted on the larger mass by the smaller mass? Let's think about this. This is very important. 2 things collide. Boom. One is huge, one is small. A little bug in a truck. Right? How long does the collision last for both of them? Is the time different? Does that make any sense? Are they colliding with each other? So the time of the collision has to be the same. Now, what do we know about Newton's laws about when things push against each other? Can I push you more than you push me? Is that possible? Right? What if we push each other? Let's say that he pushes and I push. The force he pushed combined with the force I push, and we push each other by that much. Does that make sense? You cannot push someone more than you get pushed back. Does that make sense? I'll give you an example. If I push him with 3 newtons, does that mean I got pushed back with 3 newtons? Yes. The only way, I'm not going to move backwards is this friction. Does that make sense? So, let's say, for example, you have a boxing match in ice. What happens? Every time somebody lands a punch, they lose their balance and fall. Does that make sense? Because they got pushed back. Does that make sense? Be fun to watch. Alright? Yeah, they do have that. It's called a mud fight. It's also called hockey. Yes. It's called hockey. It's very true. Right. Now, by that same token then, when something hits something else, can the force be different? No. Whatever force I impart on you, you also impart on me. Acceleration can be different, but can force be different? Now, if force is the same, and time is the same, and impulse is force times time, can the impulse be different? No. this here at number 9 as a restatement of Newton's third law. Pay attention, this is important. Basically, remember I already talked about this. The third law is basically saying that total momentum of the system cannot change. Correct? That means you cannot have an impulse within the system itself. Whatever impulse I impart on you must be imparted on me. Otherwise, you will change the momentum of the system. Therefore, this is going to show up in the as for sure in the multiple choice. You know how last time we had a bunch of scenarios like this. Well, if the force applied to this is this much, how much is the force applied to the other thing? Third law. There's always the explanation in those scenarios. Same thing over here. If I push this table with an impulse X, the table has an impulse X on me. It's the same thing. It's right. The same force over the same time. Impulse is the same. Unless, of course, a force acts from outside the system. All right. 10 we did, didn't we? We did 10? We're almost done. All right. So just a few problems. So 11. Artillery shell explodes. What kind of problem is that? An artillery shell exploding in midair. Does it look like which one? The third one. But like any other problem, it's all the same. Momentum at the start, momentum at the end. That's what we have to think about. All right? Yes?
Amanda Sardinia's going home?
Bye, Amanda. All right. So an artillery shell explodes. So this is number 4. Now, think about the artillery shell. Does it have momentum to begin with? Think about it. It's going. Does it have momentum? Of course. Let's call it mv. Right? It's got a momentum. Its mass times its velocity. But what happens to the artillery shell? It's apparently it explodes in midair into tiny little bits. So then what happens afterwards is you have these tiny little bits going in all kinds of different directions. Blah! Exploded. According to the rules of conservation of momentum, right? Momentum cannot change. So that means the total momentum of the system still has to be what? mv. Does that make sense? Of course, now you have tiny little masses going in all kinds of different directions. All right? But think about that. That's important. Okay? So let's see. Which of the following statements are true after the explosion? The total momentum of the fragments is equal to the original momentum of the shell. Does that make sense with what the rule says? Isn't that what we said? You cannot change momentum, all right, unless a force pushes it in there. Unless something starts to push the fragments, well, technically air resistance does. But forgetting that, it still needs to be the same momentum. The total kinetic energy of the fragments is equal to the original kinetic energy of the shell. Or can the fragments move faster than before? Not about mass here. It's about something else. What happens when a bomb explodes? By definition. Is there energy released there? Right. There was potential energy inside the bomb and it exploded. So can the fragments get... So if I'm a bomb and I explode, right, will it increase the kinetic energy of my fragments? Yes. But did I change the energy? No, because I have potential inside of me. Does that make sense? Now, so that means, can the fragments gain kinetic energy compared to the start? Yes, but they can't gain momentum though. Does that make sense? All right. So, yes? Same thing to put the solution so oh, do you give you the thing? 1.5? I said, what did I say, 3? I think I did the math wrong. Look at this, it's 1.5. It's 0.2%. Wait, no, wait. 300 mLs?
Yeah.
Isn't 1% 3? 1% is 3. So 2% would be 6. But it's so it should be points. Yeah, just do what they said. I don't think that's right, but just do what they said. All right. So what
you said or they said?
What they said.
Okay.
I think 2% should be like. No time to think about that. Do what they said. All right. So, what is 1.5 out of 300 people? I need to know. It's bothering me now. 1.5 divided by 300.
It's 0.005.
You see? I knew that would make sense. Now, but just do what they said. You know? So, the last one says that the total kinetic energy of the fragments is equal to right now. So no. So we decided this thing. Now I want to add a little thought to this. These fragments, are they still going to continue moving forward, even as they explode in different directions? That's how you realize that the momentum can change. Because if I'm going in midair and the thing explodes, some of the fragments get thrown backwards, some of the fragments get thrown forward, some of the fragments still throw up, some of the fragments get thrown down. But if you get the total mass of all the fragments and all the velocities and add it all up, the center of mass of all of that is still traveling exactly the same way as before. That's something that's difficult to understand. But even if the fragments split, if you take the average mass and velocity of all of them, it's still mv going the same way. Does that make sense? That's why momentum doesn't change. You're going to add, like, each individual fragment goes into a different direction, yes. But as a whole, if you take the average, the center is still doing the same thing it was doing before. You know? And that's why momentum is concerned. All right? So, now these are a bunch of math problems. Can you turn this to me, please? Because I'm going to do it over here. I'm just going to do a couple, and then we're done. So, this one is a type 1 problem. I'm going to show you how to do it. This is going to show up for sure. All right? A batter hits. Remember how we do physics problems. As we read through it, we identify things they're giving it to us. A batter is hitting a baseball, 0.4 kilograms. So I write that. Mass equals 0.4 kilograms. All right? Actually, for the sake of sig figs, I write 0.40. All right? And it says it was approaching him with a speed of 0.0 meters per second. So that's the velocity of the ball at first. 30.0 meters per second. All right? As a result, the ball leaves the bat at 40 meters per second in the direction of the pitcher. So let's think about that. 40 meters per second. But let's think about the sign. This is why diagramming is important. The ball is coming at 30 meters per second, but then it goes back at 40 meters per second. Can I put them in the same sign? Velocity. No. One has to be negative. You can choose which way you want. If I call left positive or left negative, if I call left negative, then this has to be negative, and that has to be positive. Does that make sense? Otherwise, I'll get the answer wrong. Now they say this collision that happens with the bat lasts 2 milliseconds, right? So the time they're giving me here is 2 milliseconds. Now remember, when I see milli, I basically do this. All right? That's what that m means. All right? If I see kilo, it means 10 to the third. That's a milli is 10 to the negative 3. All right? What is the average force exerted by the bat? So this is why you do problems like this. Because look at what it's telling you. Mass 1, the mass, 2 velocities, time, and force. So now I look for a set of equations that can help you with this. Something that has 2 velocities, mass, force, and time. So you see what I'm going to need? This together with that. Right? We'll solve the problem. So the next step is identifying the equation that I need. And I'll do that. Force times equals mass times velocity final minus velocity initial. And then my next step is anything that's 0, I cancel out. There's nothing 0 here. So the next step is solving for what they want. What do they want to know? Force, right? So I solve for force. Force equals mass. I just divided by a delta t to get this. Notice, by the way, that this is acceleration, right? Velocity over time. So they're just asking answer because I may, really. All right? But anyways, the force. Now I just plug it in. That's the next step. 0.40 kilograms with this. So you can do dimensional analysis. Velocity final is 40 meters per second. Velocity initial is minus, but there's a minus velocity as well. 30 meters. This is important. If you don't put that minus in here, you get the whole thing wrong. You see what I'm saying? The minus is there, but there was a minus here. So you got to be careful. Right? Divided by time, which is 2 times 10 to the negative 3 seconds. And then just plug it in and solve the problem. And that's it. All right? The next thing is just computing the solution. Now notice, by the way, this is in meters per second, and that's seconds on the bottom. So that means I'm going to get meters per second squared, all right, on the bottom. And this is kilograms. So it's going to be kilograms meters per second squared. That's MA, newtons. force. Right? It makes sense. So dimensional analysis tells me that I did the setup right. And as far as the numbers is concerned, that's basically 70 divided by 2, which is 35. Right? There's 10 to the negative 3 in the bottom. That's like having 10 to the third in the top. Right? So that's 70 divided by 2, 35. So it's 35 times 10 to the third, but then it's times 0.4. Right? Which is 2 decimals lost over here, so just times 10. Right? Because this is like 10 to the negative 2. Right? So just 4 times 35, which is 120. 4 times 5 is 20, so 140. Did it? All right? I don't know if I did it right. You figure it out. But I think I did. All right? That's how you, now with number 6 figs being 2 or 3, that would be an acceptable answer. All right? So, do you understand what this is a first type problem. I'm going to do one more. That's to do with a collision. 17. The rest is just whatever. Because we don't want it in the middle of math class. But I'd like to show at least one little bit. So 17, same process. We solve physics problems the same way. A 2-gram bullet. What is the standard unit for mass? Grams or kilograms? Kilograms. All right, so that's important. So they give you the mass of the bullet in grams. I need to have it in kilograms. So that's 2 times 10 to the negative 3 kilograms. Because that's what a gram is. 1,000 times smaller than a kilogram. All right? And the bullet was traveling, so I have the velocity of the bullet, initial velocity of the bullet, which is 700 meters per second. That's standard SI unit. Don't need to convert anything. It becomes embedded in a stationary block. All right? I'm going to call the block, it's also a B. So I'll just call it O for object that it hits, okay? So the velocity of the object initially is 0 meters per second. How do I know that? Because it says stationary. You see that, right? It says stationary. They also give me the mass of the object to be 5 kilograms. Right? 5.00 kilograms. They ask you what is the speed of the block, right, after. Now here's where you got to be tricky, because the bullet stops moving. It gets embedded in the block. That's important. So at the end, what's going to be moving is the bullet and the block together. What kind of problem is that? It's like 2A there. Does that make sense? So that means this velocity is not just really the velocity of the block. It's like the velocity of the object and the bullet together. They're going to be one. Right? Okay, so remember that. All right, so now how do I do these kinds of problems? Whenever you have collisions, bouncing back, splits, it's always the same thing. Change in momentum is 0, which means the momentum I have at first has to be equal to momentum I have at the end. Right? So let's think about the momentum I have at first. The momentum of each object. Well, the block has no momentum because it's stationary. Right? It's V0. But the bullet has momentum. It's going to be this times this. All right? So it's going to be the mass of the bullet times the velocity of the bullet. What about momentum after? The block and the bullet become one. So that's the kind of situation when I have to do this. The mass of the block plus the mass of the bullet, right, are going to be traveling together at the speed that I want to find out. And that's what I want to find out. So my next step is to cancel all the zeros. There's no zero. The next step is to divide so that I solve for that. So all I have to do is divide both sides by this. And I'm going to get mass of the bullet times velocity of the bullet at first, divided by the combined masses of both objects, should give me the velocities that I want. And now you just plug it in. So I'm going to do the plug-in step on this side. You see, they're all the same thing. Plug-in step on this side. So then mass of the block is 2 times 10 to the negative 3 kilograms times velocity of the bullet at the start, which is 700 meters per second, divided by the combined mass of both objects, which is 2 times 10 to the negative 3 kilograms, plus the mass of the huge object, which is 5 kilograms. To be honest, the mass of the bullet will barely affect things. You know what I'm saying? Barely affect things, because the bullet is so tiny that when you add this to this, you're not really even adding anything. right? So this just becomes 700 times 2, which is 1400. But it's times 10 to the negative 3, so I just put 1, 2, 3. So on the top I have 1.4. Right? If I did this right. And on the bottom, it's kind of like 5.002. Right? So it's really just the block that really matters. So when you do that, what is the velocity of the block? No, not really, 0.
The velocity of the block.
No, afterwards, in the bullet. Because you see, this is what we're solving for. Point what?
0.279288804.
Alright, so to 6 figs, which is 2, would be 2.28. 2 point? No, this is 1.4 divided by 5. It's got to be a decimal.
It looks like a 14.
It's 1.4. Or you can just plug in all of that to be sure, but I think it's that. So what do we get? By the way, I have kilograms up here and kilograms down here, so the kilograms cancel out and I end up with just meters per second. That's a velocity, so it's the right thing. Right? So I did what I'm supposed to do. What is the velocity, guys? Point to what? 0.28? Okay, meters per second. Now, when we're done, the last thing is explore limits or think about what you've learned from the problem. It doesn't make sense for a very fast traveling bullet to hit a very massive object and then it causes the object to barely move afterwards. Does that make sense? Yes, because the object is much heavier than the bullet was. Right? Now, what did I learn from that? If you've seen the Hollywood movies when people get shot and they go bah, 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 and fall like that, does that make sense? No, because that bullet, although it's going to cause a massive impulse and a lot of pressure, therefore it's going to perforate through you, especially if it doesn't go through you, if it becomes part of you, right? That's all actually going to slow down even more. If it goes through you, its mass does not contribute to slowing you down, which means that actually you go even a little faster. But even if it does or doesn't become part of you, it's such a tiny little mass that's not making a difference. Really, because you're so massive, you're not 5 kilograms, you're like 90 kilograms. And this bullet, even if it's a rifle going at 1,400 meters per second, supersonic, right? It still won't, let's say you double the speed, a supersonic rifle, you know those big ones? Bah! You know the really nasty ones, right? Twice that speed. By the way, the speed of sound is like 300, so this is already supersonic. This is 350. This is twice the speed of sound. Let's say you double that. So you're going at Mach 4. I'm talking about those, enormous rifles to get that little bullet to go really fast. Even then, double that. This block would only have gone at 0.5 meters per second. That's like, right? So it barely pushes the thing backwards. But you're not a block. You're like 40 times this, not 40 times, like 20 times this weight. So that means you're barely going to move. Like literally, you're going to hit by that and you're going to just fall where you are. That's how people get shot. Right? So Hollywood just makes it look like, crazy. But when you get shot, and you fall. That's it.
What about when you get hit by a sniper?
That's what I'm talking about. That's what I'm talking about. The math doesn't make sense. Huh?
Can you laugh like that, please? Please.
Who volunteered to get shot?
I volunteer.
Now, well, we could do it actually.
Look,
We
several
could do it.
Yeah, several
Not Nerf
times.
guns. We could do it with a paintball gun. You just sit there, and we measure the mass of the paintball, and you shoot you. And then you see what happens. Hey, by the way, remember that this is. Hey, remember also. But remember also that you do not move for 0.28 really in a real situation because that requires no friction. Remember we talked about this? The moment there's friction, you're actually not moving at all, right? And so literally you get shot and you just fall where you are. That's what happens. No one gets shot and falls backwards. That doesn't make any sense. You do get fall backwards when you're shooting things, though, right? So especially if you have the wrong shoes. If you're shooting guns with the wrong shoes in the wrong place, like this would be a bad place to shoot a gun. You might actually lose your footing, if you have the wrong shoes on.
Yeah, so now if someone comes to shoot at the school, they're like, I got the right shoes on.
I won't
Ow.
Yeah, that's why you also get yourself in a position to actually stop the friction. You know what I'm saying? Because if you look at soldiers, they actually have to have grip, right? And that's part of the reason. Like seriously, you're shooting a rifle, you're not going to be able to do it if you don't have grip. You know? So, all right, guys. 25 minutes, 20 minutes left or so. Practice for momentum or collisions, whichever one you want to do. I just want to point out that I do have momentum and collision lab apparatus here. Lots of cool stuff. For example, you can use a track and two carts and colliding with each other, calculate this, basically do collisions. I also have these carts that have fans on the bottom. So when you collide them with each other, they have no friction, kind of. So you can see how inelastic collision is kind of supposed to look like.
You have the
Uh,
balloons that you can run into each other?
What do you mean?
No, this is the economy just runs.
That would be a cool interesting lab. Either way, look at the projects and activities for, maybe not for this class, but for the next two classes. Look at the projects and activities for ideas for labs. You can do collisions with the cars if you want to. You can do whatever you want with that. Or you can just do what you always do. But 2.5 days left for practice, okay? So I am not counting today's practice against you, so these 25 minutes, catch up. All right? Catch up on points. Yes.
I have a question.
Yes.
For the total between total and BMX speed, for experience points,